So in our lesson last time, no, so we covered this, no? So we call this as the center of gravity, and we know that we can find the center of gravity by some process or method. And this method of finding it now involves cutting the figure. No, if the figure is not uniform, no, if it's not regular in shape, no, like of course, no, like what I have here in my hand, no. So this is, I call this basically as a composite figure. So if the figure is not perfect, no, like a square or a rectangle, then we have other means of finding it, no. So but the point is, no, we have to agree first, no, so that we will have the same coordinate value. We have to agree uh, about the about the way we hold this, no, and the way we solve, no, the composite figure if it's made like this, no. So we have to agree first how we position this one, no, in our Cartesian plane, no. You'll notice that the value of the Cartesian plane, no, will eventually change its coordinate every time we change the position of the figure. Hopefully now you are seeing the one that I'm holding, no? So again, no, I call this as a composite figure. So the center of mass or center of gravity again, no, is a location. So this is where the whole weight of the body is believed to be concentrated, no? And with that in mind, we are able to balance the body if we know where it is located. Now, other than that, now we talk about the momentum, no? So the momentum is the product of the mass and the velocity of the body, no? We basically call, or we symbolize momentum with letter P. So momentum for P, no, or there's a triangle before P, and we multiply it with the mass of the body and the velocity of the body, no? So um, we get the product of M and V, and again V is our velocity, no? So M here is our mass, while V is the velocity. So therefore, since we are dealing with velocity here, no, and not merely speed, we can consider our momentum to be also, no, a vector quantity. It's sensitive to the direction as well, no? So our unit for our momentum will be in kilogram meter per second, no? And we understand that there are several ways, no, with which, or there are two factors that affect the value of the momentum, no? So if the body is so big, its momentum is likewise big by virtue of its mass. If the if the body is traveling at a high speed, no, even though its mass is small, but then, no, we will see that its momentum will also be large, no. So like a bullet, for example, it's not very massive, no, it's so small, but despite that, no, it can create uh, so much destruction. It can kill, no, because of its sheer speed, no. So its speed is so fast that it can penetrate through armor, no, body armor, through metallic, no, armor, and so on, no? So again, no, momentum, no? So Ilonggo pa, we call it as ang builo, no? Ang builo sa isa ka object, no? Okay, and then, no, we let me erase this, no? So um, here are examples that we tried last time, no? And we simply, no, get the difference. So if we are to find the change in the momentum, no? So the change in the momentum is the difference of the final velocity minus the initial velocity times its mass, no? And we indicate the change in the momentum, no? So there will be change in the momentum when the object, no, will encounter an obstacle. So if for example, no, two billiard ball, no, will hit each other, there's going to be a change in momentum in the billiard ball. No? So if one ball is steady or at rest, and then the other is moving, no, you'll realize that both of them will change their momentum when they collide. No? When they collide, so it's possible that after collision, no, one of them will stop moving, the other one will change direction, or both of them will move, no, but they will change their speed. No? So again, in the case of a billiard ball, no? So Efren Bata Reyes, I think you're familiar with him. He's very good at using the knowledge in momentum, probably, no, how he makes his uh game there, no, so perfect. Sometimes you'll see it, no, he'll do some tricks by making the ball, no, there, no, move at a particular direction, no, that is not done, no, by any ordinary guy, no. So but anyway, change in momentum. So we have this symbol delta P, no, I call it delta P, this triangle beside letter P, no? So you can try these sample problems here. And then we go to a thing we call as impulse. No? And again, impulse, but in this case, no, I'll symbolize impulse with letter I. No? So impulse I is equals to the product of the force times the time, no, that force was created. No? Um, so again, no, when a car collides, no, to a certain structure, or that car collide with another car, you'll realize that uh, there's going to be a big damage, no, a huge damage that is created on the car. No? I've seen some cars nga na bunggo sa pader, no, nga nakita nyo sa along the way, no, that hits a pavement, no, that is not moving. You'll realize that the that the that the car, no, especially ang iya nga the place where the engine is located, no, nga nagakaguba siya, no. So again, no, what created that damage? Why is there such huge damage in the car? Again, because of the force, guys, no, that is suddenly created, no, in a fraction of a second, no. So if the car has a huge momentum, that momentum will eventually create that force, no. So if the force is so big, no, because of its huge momentum initially, no, then the damage will be, no, so large, no. So again, no, because the force there is in several thousands of Newton, and the time is just a matter of, no, a very small fraction of a second, no? So how fast will an accident happen? Again, no, it can happen in a snap, no? Nobody can really prepare for it, no? So again, that's what we call momentum. Now, usually impulse and the change in the momentum can be equated, no? And therefore, no, you can see this equation over here, no, that tells us that Ft is equals to m times delta v, no, and m delta v is our change in the momentum, no. So this one is our impulse, no. So again, a moving car can create that impulse, no, once it hits, no, a certain object, no, or another object, no? So impulse is the product of the force and the time, no, that particular force was applied, no. No, okay, so since the unit of force is in Newton and that of time is in seconds, then the unit of impulse is Newton second, but it is the same as, no, so Newton second is equivalent to kilogram meter per second, which is the unit of our momentum, no? So impulse is a vector quantity, no? So the same as momentum, no? So since they are being equated, then most likely, no, both impulse and momentum are vector quantities, no? Okay, another example, no, in baseball, when a pitcher exerts a great force, no, on the ball, then extends the time of contact, no, as much as possible so that the change in momentum of the ball occurs, there is an increase in its momentum, no? So the pitcher, no, will throw the ball towards the guy who will strike the ball, no? So where is the impulse there, no? By the time when the ball hits the bat, no? So that's where the impulse is created. But the momentum there, no, is when the pitcher, no, extends his hand backward and then he throws the ball suddenly, no? So after releasing the ball, that ball will now fly, you know, so fast. Now again, in a baseball game, no, there are pitchers there that are so extraordinary. They can throw the ball very very fast. No? So again, no, I don't know, no, if everybody can do that. No? But again, there are some guy, you know, in that game that can throw it so fast. No? They time the I don't know the pitch, no, or the way they throw the ball, no? And the way they measure it, no, it travels, no, just like, no, a very fast car, no. So again, no, that's where the momentum is created, no. And again, the impulse is made when it strikes the ball already, the bat, no. Okay, so we have this, no. So this is our the momentum of an object can be lessened in two ways, no? Again, by decreasing the force over a long period of time, and then, no, by decreasing the force over a short period of time, no? So again, no, now here are our exercises, and again, we have some equations earlier, and I believe now I can assign this to you. No, I am going to pause for a while our recording, no, while you look at this, no. So everyone, no, you can have a try for this one first, no. So again, now let me post this for a while, no? Okay, so we are now going into lesson 6.1, no? And 6.1 is on equilibrium. I think our first lesson there, lesson 6, was also called equilibrium, no? So equilibrium again is a word that we can probably cut into two sections, or equal, no? And then this word na brium siguro, no? So we can have, no, equal or balance, no? This is a state of balance, ang atong word na equilibrium. So we have here our figure, no, which is basically a balanced state, no? So we have a rock there, no? So some guy is fond of doing or creating this one, no? So they put up some rocks and then they can have it, no, for so long until somebody disturbs it, no? So this is a state of balance, no? So paano tani nakuha ang ining balance ang sining bato, no? So they've probably located the center of gravity of these sets of rocks, no, sa babaw, no? And they put the object below as a kind of a fulcrum, no? I will emphasize the word fulcrum. So this one is the one that balances the rocks above, no? So fulcrum ang dalom, the location of the center of gravity was determined, no? So the CG there is crucial, no, in balancing this whole thing, no? So you could never balance this unless you locate the center of gravity of the stones above or the rock above, no? Now there are two conditions, no, for equilibrium to occur. Actually, now there are two, no? So we can literally divide, no, the conditions for equilibrium as the first condition and the second conditions of equilibrium. No? So there's what we call, no, the first and second condition for equilibrium. No? So equilibrium will not occur until these two conditions are basically satisfied. No? And there are two conditions that has to be satisfied. No? A very common effect of force or a set of forces now acting on a body is to change the state of motion of the body. No? So from rest, for example, to a moving condition, that is not equilibrium. No? So you change its state. No? Changing the state of a motion of a body means changing its velocity. No? It may happen that the resultant of the forces acting on a body is zero, so there is no change in its state of motion. Now, however, now if we will apply forces on a body, and eventually, these forces, adds up together, and it still, results to a net force nga zero, then we will realize nga what we achieved there, is a body that will remain in equilibrium, or a body that will remain at rest. So is it possible that only one force acts on a body? Have we answered that question before? Christian, can we keep or can we apply only a single force on a body? Is that possible?
No, sir.
Yes or no?
No, sir.
No, no. So as I sit right now, there's at least two forces acting on me. Either my weight, acts on the floor or on the chair, and the chair, will now push me up. So there's at least two forces acting on me. So hindi pwede nga isa lang. So but however, why is it that I'm still not moving vertically? Because these two forces are simply equal to each other. They add up to a thing or a total net force na zero. So when the forces acting on me, like my weight and the normal force, are equal and they are opposite, they add up to zero. Therefore, my body will remain in the same state, at rest. Again, that's one example of equilibrium. So when the forces there happens to be zero, we can say that the body is in equilibrium under the actions of the set of forces. However, the forces there should add up to zero. Maybe here are illustrations. When all the forces that act upon an object are balanced. So when we say the word balance here, ang force nga nagapasaka kag ang force nga nagapanaog equal lang. So pila ang difference nila? If 50 is subtracted by 50, pila difference nila? 50 minus 50, the difference
Zero.
0. Ang nagapatuo minus ang nagapawala, 30. Ang nagapatuo, 30 man nagapawala. Pila difference ang horizontal forces?
Zero.
So ang tawag ta sang forces during a zero, we call it as balance forces. We term it as a balance force, because the body will remain at rest. Now what if one of the force that goes up is bigger than the force that goes down? What will happen to this body? So if the one going up is 70 instead of 50, what will happen to the body? Will the body go up or will it remain horizontal? Will it remain in its place?
Your body will go up.
When the force going up is larger, then this one will now start to move upward. So is it still balance forces ang involved? So this time hindi na. So we call it as unbalanced forces when one of the force here is greater than the other force in the same axis. So it has a tendency to either move to the right or left when one of the forces horizontally is greater than the other. So this, however, does not necessarily mean that all forces are equal to each other. In a figure, the two objects are at equilibrium because the forces that act upon them are called balance forces. So again, so here, no, is another illustration probably, no. So we usually deal with our figure, no. We combine all horizontal forces together and we combine all vertical forces together to know, no, whether the forces on the axis are balanced or not, no. A familiar case of equilibrium, no, is a book that is at rest on top of a table, no. So the force that goes up is known as normal force. The force that goes down is known as the weight of the body. If the two are equal, then of course the book will be at rest vertically. Na? This book will not go up and down. Na? It will just stay on the table. And from the time where you left it, nakakagang time na nabalikan mo siya, ara lang ang libro. Na? So the book will not move because it is in equilibrium condition. Na? Now there are two forces acting on the book. Na? So again, no, we see that one already. Na? So the vector sum along the vertical axis is 0. Are you following me? Do you have a question?
None, sir.
No question. So another example is the case now where an object is in motion and is subject to two equal but opposite forces. No? So, so it is moving, no? But if the two forces here happens to be equal also, then this car, no, even though it's moving, will also be in a state of equilibrium gyapon if F1 and F2 are equal in value, supposing there are only two forces involved here, no? Despite the fact that this is already in motion. Okay, may velocity siya. No? Now, if the forces there happens to be equal to each other, no, in opposite direction, then there would be no net force, so no acceleration also will occur. No? So if there's no acceleration, then the body there is in a state of equilibrium. No? We call this as uniform motion. No? So equilibrium condition, managyapon ng uniform motion. No? Unless otherwise, no, one of the forces there is greater than the other, then therefore the body there will increase its speed. No? Pwede siya nga mag-accelerate kung lain na karan ng iyang forces dira. No? So if there's a resultant force that is not zero anymore, then the car will increase its speed. No? So the car does not change its state of motion since its velocity remains the same and is therefore in equilibrium. So dua ka conditions ang equilibrium. Pwede nga at rest, pwede man nga it is in motion. No? Okay, so we basically have a remainder of time na lang ang mga 3 minutes. No? So if you are cut, no, please follow the discussion or follow the link lang karan. No? Okay, so here are some definitions. Equilibrium is a state of rest or balance, no? Due to the equal actions of opposing forces. No? A force is a physical quantity that denotes ability to push or pull, no? Twist, no? Pwede man nga para sa botilya bala, no? You twist and open the cup, no? So that is still a force. We call that as a torsion. No? A push is, maybe you can call it compression. No, you push an object together. No, so you make it smaller. So compression, or you can also pull them apart. No, so pulling objects apart, guys. No, is known as tension. No, you stretch it. So we can apply forces in several ways. No, now our motions can result, no, either in translational motion. So from A, masaylo siya sa B, no? So it will move from A to B. That's translational motion. Or a motion can also be done in circular manner, no? Nagalibot siya, no? So our motions can be of two types, no? So pwede nga ang body, no? We can say that the body never leaves its place like an electric fan nga blade, no? The electric fan blade is, we know that it never leaves point A, no? Ang electric fan na tupad ko di subong, it's there, no? After 2 hours of teaching, for example. But is the fan at rest? Is the electric fan at rest?
No, sir.
You know that the blades of the fan never stops moving, so we can never say that it is at rest, no? So, however, it does not transfer. So we call it rotational motion, or sometimes, no, there are other motions nga ginatawag naton nga circular motion, no? Now, inang nagatiyog guys nga blade sa aton fan, we can call the action sang force dira that causes the rotation as torque, no? So ang nagalibot nga blade, no, na fan, naga-create na siya sang torque na ginatawag, no? So a torque is a rotational or twisting effect of a force, no? So if you apply the force in two separate directions, then you can make it rotate, no? Now we are going to be cut in a few seconds, so kindly stand by and click the link next, no?